Chapter 5 is all about exponential and logarithmic functions. Before we can actually look at exponential and logarithmic functions, though, we are going to have to talk about a couple of things. First, section 5.1, composite functions, and then after that we're going to look at one-to-one and inverse functions in section 5.2. So what is a composite function? Well, if we have two functions, if f and g are functions, then we define the composite function f of g as f of g of x. That's equal to f of g of x. So this little circle, it's not a dot, it's a circle, and it's floating it, up in the middle between f and g. You can read it as composed with or of, right? So we could say f composed with g or f of g, right? And basically it's defined as taking g of x and plugging it into f of x. So we're plugging g of x into f of x. And that's going to give us a new function. Okay, let's look at an example. We're going to let f of x equal x squared and g of x equal x plus 2. All right. The function f of g of x is the same thing as taking g of x and plugging it into f everywhere there's an x. So I'm going to write a little interim step. We're going to say f of g of x is the same thing as f of x plus 2. Notice I'm plugging in x plus 2 for g of x because that's what g of x is, right? Now I'm going to take this x plus 2 here and plug it into f everywhere I see an x. So this will end up being x plus 2 squared. Since f of x is x squared, when I plug g of x, x plus 2, into it, I get x plus 2 squared. So that's what we're talking about if we're composing functions, or if we're looking for a composite function. We're plugging one function into another function. Okay? Now, the domain of a composite function, domain of a composite function that is composed f composed with g, so g plugged into f, turns out is the set of all numbers x in the domain of g such that g of x is in the domain of f. The idea is that the inputs into the inner function, or g, as long as they give outputs from the whole function, f of g, give us the domain of our composite function. All right. Well, I'm going to draw a picture of this idea. Okay. So let's say that we have a set here, right, that is the domain of it's the domain of g. Okay, our inner function, right? Remember, we're looking at the idea of f of g, which is taking g, plugging it into f. So this area is going to represent the domain of g. this area is going to represent the range of G. Okay? So if we have some number, let's call it x, in the domain of G, and we use G to take it, so here's our function G, it's taking x to some value G of x, which is in the range of G, right? If that G of x is also in a new circle here that I'm going to call the domain of F, meaning if it's in the domain of F, it has a value taken by F from its domain to its range. So we would call this F of G of x. So since this x ultimately gave us a value in F of G of x by the function F of G, right? We would say that this x is in the domain of F of G. All right. Now, let's take a second x in the domain of G, right? And G is going to take it, the function G is going to take it to another value in the range of G. And then let's say that that G of x, since it's sitting here and not inside, I'm going to put in red, this is the domain of F, right? Right? Since it's not in the domain of F, this G of x right here, it's not going to get taken to over here, which is the range of F, by F, right? So this x right here is not, so we're going to say this is not in the domain of FG, and this one here is in the domain of F of G. Okay, so that's kind of a picture of what's happening. Now, how can we find domains of composite functions? Well, it's actually quite easy. We're going to say that, or what turns out is that the domain of a composite F of G is equal to all the x values on which G of x is defined, right, intersected with the x's on which F of G of x is defined. So that's exactly the x's that behave in the way that this x that I've just circled in the blue behaves, right? It's an x on which G of x is defined, meaning that it takes us to a G of x value, and we're intersecting it with the x's on which F of G is defined. So notice we have G that takes this x to G, and we have F of G that takes this x to F of G. Okay, so that's in the domain. All right, let's look at an example of composing two functions and talk about how to find its domain. All right, so I've got the example. We're going to let f of x equal 1 over x plus 2 and g of x equal 4 over x minus 1. Okay. We're going to find f of g of x and its domain. Okay. Well, the composite function f of g of x is the same thing as f of g of x. So we're going to take g of x and plug it into f. So that means we're taking 4 over x minus 1 and plugging it into f. Now the only spot in f where there's an x is here in the denominator. So that's where I'm going to put my g of x. So I end up with 1 over 4 over x minus 1 plus 2. Alright, now we do need to simplify this because it's not in a very simple form. Working in the denominator, if I want to get a common denominator between those two terms, I can see, well, it's going to be x minus 1, so I need to multiply by x minus 1 on the top, x minus 1 on the bottom of the 2. Then we can add 4, the numerators, 4 plus, I'm going to go ahead and distribute while I'm at it, so 4 plus 2x minus 2 over x minus 1. And here we're saying 1 is being divided by this fraction, so that's 1 times its reciprocal, which is just its reciprocal. And combining the 4 minus the 2 is the 2 plus 2x. So this function is f of g of x. Okay? Alright, so I've found the composite function. Now I'm going to look about its domain. Okay? Now the domain of f of g will be the x's on which g is defined intersected with the x's on which f of g is defined, right? That's the same thing as saying the domain of g, which is g is 4 over x minus 1, intersected with the domain of the final function x minus 1 over 2 plus 2x. Alright, so what is the domain of 4 over x minus 1? Well, it's all x's such that x doesn't equal 1, right? We're going to intersect that with the domain of x minus 1 over 2 plus 2x. Well, we know that in this function, the denominator 2 plus 2x cannot equal 0. So what that means is that 2x cannot equal negative 2, or x cannot equal negative 1. So our domain of that composite, of that new function that we got, is all x such that x does not equal a negative 1. Now let's look at their intersection. Where do these two intervals intersect? This is all real numbers except for 1, and this is all real numbers except for negative 1. So their intersection over their overlap will be all x such that x is not negative 1 or 1. Okay? Now, take a look again at our composite function, f of g of x. It ended up that it was x minus 1 over 2 plus 2x. And you might say, well, if I look here, the domain does not include negative 1, but it includes 1, so why is 1 not in the domain of f of g of x? Well, remember, it's not in the domain of g, right? It's not in the domain of the original function that we plugged in, right? So it's not in the domain here of g. So if there's a number that's not in the domain of a function that's being plugged into another one, I mean, the original function that you're plugging in, this inner one, is not even defined on that. So it can't be even an option for the composite function. That's why we have to look at the intersection and we don't include 1 also in that domain.